Cool. We have a decent amount of people, so I'll just get started. Hey everyone, my name is Nick, and I'll be presenting an introduction to JAX. And so for contact information, you have my Twitter here, and no email. You guys just have to follow me on Twitter. That's your only option. I guess in terms of setting up this workshop, please feel free to interrupt me at any time or at any point. You can also message the chat. I'll try my best to keep an eye on the chat, which is kind of on the side of my screen. Feel free to message questions there, or just unmute yourself and ask. It's all good. So our overall workshop goal today is to introduce JAX, but also to create like a JAX user group or community at Waterloo. You guys don't know what JAX is yet, but hopefully once you find out, you'll think it's cool enough that you'll want to continue using it. And it's great to have a group of people within the DSC that you can reach out to work on projects together or ask for help. And so ultimately at the end of this workshop, we want people to be interested and work on things together. With that being said, I am not an expert at all. I'm just an enthusiast. Really, I'm just a couple of months ahead of you guys who are starting to learn it now. And so hopefully that won't reflect in the presentation, but this is great because we can form like this user group and help each other out and see how that goes. So I'm going to start with prereqs. I was really hoping the thumbs up feature would work because then I could see who agrees or disagrees with things I'm about to ask. I don't know how to do this. So okay, anyway, so in terms of prereqs, is everyone familiar with Python? Is there anyone who hasn't used Python before or has very little experience in Python? You can message the chat or actually, let me take a moment to figure out this thumbs up thing because I think it'll be super useful. Okay, yeah, that's not going to work out. Okay, that's fine. Raising the, oh, cool. Yo, how do you raise your hand? Bill, could you try raising your hand? I want to see if I see that on my end. Awesome. Okay, yeah, that's perfect. Thank you. Okay. Yeah, so if I ask questions and I ask for feedback, just raise your hand if it's a yes, and nothing if it's a no, and then I'll like wait until people say yes. Okay, so the next prereq is like numpy. So there's not really a prereq. I'm just curious to see how to target this workshop. Who's used numpy before? So I'm seeing 3, 4, 5 hands, 6. Okay, so I'm assuming either the last 5 people are like away from keyboard or don't have numpy experience. Okay, cool. So it looks like a majority of people have numpy experience, which is great, which is what I was hoping for. So this is kind of the minimum set of things I would hope that you're familiar with for this workshop. I'll give an overview of what numpy is if you don't know anyway later on. The last thing, which maybe not all of you have experience with, is like TensorFlow, PyTorch, AutoGrad. Who has experience using any one of these libraries, even if you've just seen code from libraries like these? 2 people, 3. Great, okay. That's kind of the mix I expected. Awesome, now we'll get going with the workshop. So just an overview of what we're going to cover today. The first thing is we're going to talk about what JAX is. Then we're going to get into like a mini demo of just the basic high-level features. And then we're going to talk about some specifics. So first of all, I'm going to talk about something called pure functions. And the second thing is JIT and XLA, which I don't expect you to know now, but hopefully you'll know very well by the end of the presentation. The next part is the bulk of the workshop, where we'll be going over like a simple machine learning example using JAX and using some of the features that it has. We'll talk about what makes JAX different from TensorFlow and PyTorch, because those are probably the most popular libraries that people use for the tasks I'm going to show you today. And finally, we'll go over some other resources you can look to after this workshop. So what is JAX? So JAX is essentially NumPy plus automatic differentiation on accelerators. So I'll break down what that means. NumPy is a library in Python which allows you to do numeric computing. And so essentially it allows you to deal with large arrays of data in memory and manipulate them very efficiently and to accomplish tasks such as scientific computing and other such things you may need to do with numbers. Automatic differentiation is something that's very common in machine learning. And the idea is basically if you write some functions, you want to be able to take derivatives of these functions. And you will see why this is important later on. And JAX supports this, and it has great support for this. And finally, JAX runs on accelerators. And accelerators are things like GPUs and TPUs. So typically, if you run a Python program or if you're working in NumPy, you're only taking advantage of your computer's CPU. But when you're using JAX, you can use some of these accelerators like GPUs and TPUs, which are essentially devices that allow you to do things in a lot more using much more parallelized code, and it'll run much faster. This is very useful for machine learning applications. And so the great thing about JAX is, like many other automatic differentiation systems, you can write some arbitrary program code, whether it's loops, recursion, anything else, which we'll see coming up, and you can just take derivatives through all these constructs. And JAX often is marketed as composable function transformations or composable pure function transformations. And hopefully my demo coming up will show you what that means. So yeah, we'll jump into the demo. And so I will be live coding. So hopefully this kind of goes okay. Hold on, let me just make sure I can see everything. Okay, close enough, cool. So the interface I'm using now, is the font size large enough? Does anyone want me to change the font size here? Raise your hand if you want me to change the font size, make it bigger, smaller. Okay, I'm assuming it's okay. Oh, bigger? Bigger? I can do bigger. Is that better? Okay, looks like it's better based on no feedback. Okay, nice. Okay, so the interface I'm working in right now is something called Google Colab, and so if hold a bit more, yeah. Is that okay, Ashish? Any more? All right, cool. So the interface I'm working in is something called Colab, and this is basically a Jupyter notebook in your browser, but it has some pretty cool features. And so the main one is all your files are stored in Google Drive. It has a bunch of pre-installed libraries in it. And you can also choose to accelerate your code using GPUs, TPUs. Well, those are the only two options. So either have a CPU, a GPU, or a TPU. And this is super helpful. It's free, and it lets you run code using this accelerator for like 12 hours a day or something, whereas normally you pay per the hour. So very simple. How do you import JAX? It's very simple. It's just import JAX. That's pretty much it. Welcome to your first step of the library. And so I mentioned that JAX is, oh, why is this moving so slowly? Okay, we're good. So I mentioned JAX has an interface that's very similar to NumPy. And so actually within JAX, there's a jax.numpy package, which we'll import as follows. Okay. And you'll see it's like very similar to how you do things in NumPy. So you can make arrays. So this is just a simple scalar. And so what you end up getting is an object called a device array. And so this is like a JAX array that lives in memory. And you get something with a data type and values. And so you can also make arrays like you'd expect. Which looks like this. So again, exactly what you'd expect if you're familiar with NumPy. And if you're not familiar, you can just think of that as an array in any programming language, and you can do something like whatever. You can create more arrays. So first, we're going to take a look at what these composable function transformations are, which are the most important part of JAX. And to do that, first, we're going to define some function f, which takes in a, b, and x. And it's very simple. We're just going to return a times the dot product of b and x. And so it's pretty simple. Given a, b, and x, we get out the scalar value 72, which is the dot product. And I hope you're convinced that this math is right. So any questions about things I've done so far? This is just kind of introducing what JAX is. Yeah, lovely. Okay. So the first thing I'm going to talk about is automatic differentiation, which I said was the like the most important part of kind of some of these machine learning applications. So I'm just going to create a segment called grad, and it's very simple. So we have this function called jax.grad. We give it a function, and ultimately this returns a function. And so this is the gradient function of the gradient of f with respect to your parameters. And so given a, b, and c, a, b, and x, so this is actually the gradient of your, it's like the derivative of your function f with respect to a. And so you can actually change which arguments you're taking the derivative with respect to. So for example, I don't want to take a derivative with respect to a, I want to take it with respect to b. And so I can actually pass this argnums function and take a derivative with respect to b. And so it's telling us, I hope everyone knows what a derivative is, or else it's going to be tough for the rest of this. Any questions about what I've done so far? You can raise your hand if any. Cool. And yeah, so it's super convenient, and you can do stuff like taking derivatives with respect to multiple arguments. For example, first and second, so that's b and x, and you pass in b and x, and it's an error, which is really unfortunate. Oh, I need 3 things here. And you have a derivative with respect to 2 values, so super simple. That's like the most basic and most commonly used function transformation, but there's a lot of useful ones. So if anyone here is familiar with PyTorch or TensorFlow, you will know that in often machine learning applications, you deal with batches of data. So that is, if you have multiple examples that you want to do the exact same processing over. And it's very tedious to write code that supports batches because you always have to be thinking about that. So this is a function that is called vmap. It's called a vectorized map, and essentially it automatically batches your code. So the way we've written this function f here is just supporting 1a, 1b, and 1x. So in Python, so let's say you want to have a batch of x's instead. So let's say you have 1, 1, 1, and then you have like 2, 2, 2, or 5, it doesn't matter. Right. And so you have this batch of data. So essentially you have 4 different arrays that are of like 3. Oh, this is int 32. I actually want the d type to be, actually it's easier just to do this. Cool. And so vmap is a super convenient function that allows you to automatically map this function. And so if you pass an f, you can then pass an a, b, and x. So I'll type the code first and then tell you what it does. Cool. So now, previously when we just had f, a, b, and x, we got one result back, which is this single scalar. Our vmap actually allows us to take in a batch of values. And so this in-axis represents which elements we're going to take a batch of. And so for example, here we're saying that no, we're just going to take one of A, we're going to take one of B, but we're going to batch X. And this 0 represents which dimension we're batching along. So here in particular, if you look at the shape of X, you'll see that the batch dimension is in the front. And so actually, if we transpose this value, then you'll see that the batch dimension is in the back. And so what if we wanted to deal with this value? Well, it's pretty simple. You can just say that the batch dimension is the first one, and then you get the exact same result. That was maybe a little bit quick. Does anyone have any questions about how that works? And so essentially, this allows us to take multiple values at once. I got a question here. Yeah, can you share the code after the workshop? Yes, I have clean versions of these notebooks that I'll share after the workshop. And there's also recorded and put on YouTube. Cool. And so the nice thing, when I said about composable functions, I meant that you could use vmap, grad, freely, and together. And so, for example, let's say I wanted the gradient. I wanted to vectorize the gradient of s. And so here, essentially, what I'm saying is I have this function, which is the derivative of x, and I want to compute this over some batch. And so, oh, this is not going to work for 0. So yeah, this is great. I can take the derivative with respect to this x, but for multiple x's all at once. And this is very fast. And so if any of you are familiar with writing code that's automatically batched, JAX's vmap is actually going to be approximately as fast as writing handwritten batched code. And I'll explain why they are able to do this a little bit later. Cool. I'm just going to show you 2 more function transformations that are really important to JAX. The next one is JIT. And so JIT stands for just-in-time compiled. And so JIT, this is kind of the magic that makes JAX really fast. And so many of you are probably familiar with working in Python. Python is quite a slow language. And even though these functions are calling faster, low-level code, you still have to run some Python layer to do multiple operations. So for example, given our function f, like this Python code still has to call this dot function and then call this multiply function. And this can have a pretty high overhead. And so what just-in-time compile does is it essentially compiles your code into some intermediate representation. And so that way it runs really fast. And so if any of you are familiar with using TensorFlow or PyTorch, this is equivalent to TF function or autograph in TensorFlow and torch script in PyTorch. And it's exactly the same. It's JAX.JIT f, and then you can pass it in your values as you expect. And so, again, this can be composed arbitrarily with all the stuff that you've done so far. And so, for example, I can JIT this entire expression, right? And then, so this whole thing is compiled before it's run. And so these are really small values, so you can't see the speed difference, but trust me, it'll be a lot faster for large amounts of data. You can also inspect exactly what's going on here. So if you do jack.make JAX first, and you get this JIT function. So just remember that all of these functions are like higher order functions. And so this JAX.JIT is returning a function, which is basically your compiled version of f. And you can actually inspect what this is doing using make JAXburg. So make JAXburg, and you pass in what your arguments would be. And you can see that this is like kind of the compiled JAX code. And so this is something, calling something called XLA in the background, and I'll explain what that is later. But yeah. So if you have any questions about JIT, I'll definitely go into more detail because this is probably the most important and one of the harder things to use. And the final thing is something called pmap. And this is also very cool. If anyone's worked with TensorFlow or PyTorch, you know it's kind of difficult to distribute your computation among many GPUs or many TPUs or whatever it is. So pmap, which stands for parallel map, basically makes this process really easy. And actually, to demonstrate this, I'm going to change this to a TPU runtime. So the TPU runtime, this will restart your notebook. I have some setup code here. Don't worry about what it does. This basically helps me connect to the TPU. And maybe I'll explain exactly what a TPU is. Could you raise your hand if you've heard of a TPU or used a TPU in the past? Cool. One. Yeah, that's what I expected. Not many people really use TPUs because they're not particularly common. So you can basically think about a TPU as a GPU that's really specialized for matrix operations, and in particular for machine learning applications. And so it's essentially a device that's produced by Google, and they use it mostly in-house, but you can also have paid access to it outside of Google, or of course you can have a free version through Colab. So if I actually list the local devices via JAX, we see that we have a bunch of TPU devices. And in particular, we have 8 different cores. And so typically, it would be very hard to make use of these cores using any kind of traditional library or, well, basically anything that you would normally use. But this pmap function makes it super easy. So we take in our function f, and then once again, we have to specify our axes. And so just like bmap, we're just going to say the batches along our, actually, we'll switch it up this time. Let's say the batches along, we're trying to split our input up along the axis. So of course, I can split this up among multiple axes as well, but I'm just showing this, for example. So let's say 3, 4, 5, just for example. So pmap will essentially do the following. Hold on. So yeah, so pmap returns something called a sharded device array. And essentially what happened here is this function set each of these values to a different core within the TPU. And so actually we can do up to 8 different values here, because it'll send each of these values to a different TPU device, and then it'll collect them together and give you the result. And this is very fast. It does some compilation under the hood as well. So we have 8 devices, and if you give it 9 values, this is going to fail, because you want to have the same number of values as you do devices. And so if you can imagine, if you do like distributed training for machine learning, this is very helpful. You can send your batches to different devices and very conveniently collect them back together. So that's like the mini demo. Does anyone have questions about the things I've done so far, except for JIT? I will explain that more going forward. Anything about pmap or vmap? well. What about the speed? If you guys think I'm going a little bit too fast, could you raise your hand?
Hey, Nick,
Yeah.
can you hear me?
Yes.
Yeah, I was going to ask, so in the D type, I see that these are like load 32s. Are those like JAX data types or like normal Python data types?
Yeah, good question. So in the backend, they're implemented as JAX data types, but you can also specify the data type here via like Python, like D type equals int, for example. And
okay, so they're using their custom data type, which just shows up as like this normal normal Python data type.
Yeah, exactly.
I mean, okay.
One thing you have to note though is, one thing is it's fixed precision. So sorry, the integers are like fixed size, and so like in Python you have unlimited integers, so that's 32-bit integers. And the other thing is in NumPy you might be used to like 64-bit floats. Like JAX does not support 64-bit floats yet. It's 32-bit, and the primary reason is for speed, and most machine learning applications use 32-bit. Any other questions?
Also, do you think we can pass in any data type, or like for example, would Torch data types work?
Oh, like changing the data type, like something like, I hope this works. Hold on. This is Googling at work. I'm pretty sure you can do jax.detype.32. No, there is a way to do it though. I'm pretty sure you can pass in a string here.
Yeah, okay. I mean, it's not a serious question, but yeah, it's okay.
Yeah. Yeah, so this is, you can basically treat the JNP interface as exactly the same as NumPy. So anything you can do in NumPy, you can pretty much do in the JAX interface. Any other questions? Cool. I will go back to slides. So I guess the things I've shown you, depending on how much you've worked with other libraries, may or may not be exciting to you. So the things like VMAP and pmap to me were a big difference when coming in from PyTorch or TensorFlow, but maybe it's something you might expect if you don't have experience with these libraries before. I'll contrast some of these differences later on. One thing I want to explain though is in order to use these function transformations, you have to deal with something called pure functions. And so the key is that these functions must not have side effects. So what do I mean by side effects? Side effects means you can't, for example, mutate your inputs. You can't change some global state. Like for example, if you have a global variable that you want to change, that's not something that's allowed within JAX. And well, yeah, that basically summarizes what a side effect is. And so one example of this would be the following. So for example, let's say you have some JAX array and you want to mutate these values, so from the 0 to the second index. Normally you could do this in something like Python, sorry, in NumPy, but in JAX, you're not allowed to do this. And I'll explain that in the coming slides. And so the alternative is you use something called this index update. So why can't you do this in JAX? The reason is JAX, as I showed you, has all these cool function transformations like taking gradients, vectorizing maps, distributing computation, compiling computation. And doing this analysis becomes really difficult when you have mutation of variables that goes on. And so you would generally have to express your computation as a pure function. And in mathematics, numerical computing, this is often not too hard. You might think that, well, if I'm doing things and making copies everywhere, this is going to be inefficient. So for example, in NumPy, you don't want to keep making copies of your array. You want to change it in place so you save memory. But usually in JAX, when you do this compilation step, it'll get rid of any extra memory usage, and so you don't have to worry about efficiency. The other thing you might say is, well, we're used to machine learning code being stable. Could I get a show of hands who's used PyTorch before again? Okay, no worries. This will still probably be clear without that. But in something like PyTorch, you might define a linear model as follows. And so you have this linear layer which has some weight and a bias that you want to train. And then during your forward pass, you are essentially doing this matrix multiply and you add the bias. And so during a simple training step, you have your model, you make your predictions, you compute your loss, and you take a derivative with respect to your loss. And then finally, you're like updating these parameters in place. And so this is like a clear source of mutation that we're very used to for machine learning code that is like not really allowed in JAX. And so hopefully my coming demo will show you how you can get around this. Any questions about what I mean by pure functions or state, or why I'm saying this is what we're used to? Cool, okay. So I mentioned that I would talk more about what XLA is and what JIT is. So XLA stands for Accelerated Linear Algebra, and this is a compiler for numerical computing. So compiler is something that takes in code and it produces some intermediate representation that's easier for the machine to process and understand. And in this case, this compiler will not only produce this intermediate representation, but it'll optimize your code, get rid of redundant operations, it'll combine operations, etc. And so JIT, which is called just-in-time compilation, is a process where it compiles your Python code during runtime. And so normally if you've coded in something like C++, you know that you have to compile your code before running. But JIT actually lets you compile your code on the fly as you run within Python. And so this has like some really great advantages, which I talked about earlier, which the first one is you have no Python overhead when you're calling these functions. They're in some intermediate representation that the computer will interpret directly. And so apart from the initial function call, within the function, you have no Python overhead. And the other great thing is it optimizes your code. And so I'll show you an example of some code optimization in the next slide, but this is really where you're getting most of your benefit. These really nice optimizations that would be very painful to write by hand. And so here's kind of a graph from TensorFlow. And so TensorFlow also has this XLA compiler built in. You're able to opt into it. It's not automatically used for you. But yeah, essentially using the XLA compiler on TensorFlow code gives you a massive improvement. So this is images per second in terms of training Resonant 50, which is a very common machine learning model. And as you can see, like you're getting like 1/3, like 33% greater performance, like maybe 1.5 times more performance, which is really great. So I'll kind of show you what a simple JIT optimization looks like. So suppose you have this following operation in NumPy. And so you have this a times x plus b, and then you're taking like the exponent of this value and you're storing it in y. Since Python is run eagerly, it has no compilation step by itself normally. This kind of decomposes into the following. First, you're multiplying a and x, and you're storing this in some temporary variable. Then you're adding this temporary to b, and then you're kind of replacing the value of the temporary variable. And finally, you're taking the exponent, and then you're assigning that to y. So this is 3 separate steps. And so each step, you're loading data from memory, you're doing computation, you're storing data back into memory. And this is slow at very large scales. But really, when passed through a compiler like XLA, you might notice that an operation, which is a multiply and add, on many GPUs, this is actually a single operation for small tensors. And so this can actually fuse this operation into one, and it'll be much more efficient and much faster. Any questions about JIT? Maybe raise your hand if you are following along and you're okay with things I said about XLA and JIT. Okay, that's half. If anyone has questions or wants me to slow down, please mention that in the chat. Anyone want me to slow down at all? And the rest of the people, especially people that didn't raise their hands, slow down? Is that a slow down? Okay, I'll kind of continue at a moderate pace. So here is a small benchmark on a CPU. So you don't have to worry about this code here. This is just some code that I've written for my own project, but essentially just know that it's some JAX code. Only interesting thing about this node is we're also making use of this JAX SciPy package. So if anyone's ever used SciPy before, JAX also has a subset of SciPy functions built in, which is great. So this function, you can think of it as a transformation of an image. So this will do a rotation and a translation of a batch of images. That's basically what it does. And here you can see the performance of this on a CPU. So this is not even on a GPU or a TPU. And the key thing to notice here is as the number of examples I'm doing in parallel increases, and so I'm going up to almost the full MNIST batch. The number of milliseconds increases linearly, which is kind of what you expect for some kind of operation like this. But the interesting thing is JAX plus this JIT compilation is 2 orders of magnitude faster than NumPy. And so this may not seem impressive to you, but if you think about it, NumPy is a package that's been around since the late 90s, and SciPy has been around since the early 2000s. And people have been working on optimizing this package for many, many years because everyone uses it. And the fact that JAX is relatively recent and can beat this with 2 orders of magnitude with this just-in-time compilation really says something about what kind of performance you can get out, even on a CPU. And so the gains you'll get on a GPU and CPU are much greater. Cool. So next we're going to go into a live machine learning example. Could you raise your hand if you're familiar with logistic regression? Or linear regression even? Cool, that looks like about half. I'm not really going to do an introduction to logistic regression, but maybe I'll just show a picture to help people understand. So suppose, is there a way to use your own GPU instead of the TPU provided by Colab using JAX? So yeah, good question. So no. Generally, in Colab, you're using whatever Google offers. Google also has a premium Colab where you get like some beefier GPUs and more time. There's also a GPU option here. If you want to use your own GPU locally when you're, I'll switch GPU. If you want to use your own GPU, there's a library called Jupyter, and Colab is based on Jupyter. And so you can use Jupyter notebooks locally and use your own GPU as you want. Hope that answers your question. Cool. Let me go over logistic regression really quick. So suppose you have the problem where you have some X variable and you're trying to predict Y, and Y is either a yes or a no. And so for example, let's say given in your x-axis, given let's say humidity, you want to predict whether it's going to rain, yes or no. And so a very simple, oh no, this image is tiny. How do I make this bigger? Okay, fine. Okay, I'm hoping you guys can all see this curve. And so essentially you can imagine that these x values could be something like humidity, and this y value from 0 to 1, where 0 represents no and 1 represents yes. A logistic regression is basically this function that you're regressing here, where above 50% is a yes, below 50% is a no. So it's basically that's the basis of logistic regression. I won't go into more detail for this workshop, but hopefully you guys will be able to follow along. So I'm going to live code this, which is maybe not the best idea, but we'll see how this goes. So this is going to be rough, but I want to show you how much easier your workflow can be using some of these function transformations instead of writing some of these things by hand. So I'm going to run this function here. You don't have to worry about what's in there, but essentially that lets me get my data much more easily. And yeah, feel free to interrupt at any time. Can you raise your hand if you've worked with Matplotlib before? Cool. Yeah. So Matplotlib is a really useful plotting library within Python. It essentially lets me make plots. I'm just going to use it to display some data for you guys. And so our data set is actually a data set called MNIST. This is actually loaded by PyTorch's MNIST in the backend, but it really doesn't matter. You just need some way of getting like numpy arrays out of this. So it's going to do some downloading, which is quick, I promise. Or I really hope it's quick. Yeah, it's quick, nice. So we can get our images and our label just like normal. You index into the second array. It's actually just a single image. And so yeah, for example, here you'll see that this is a 5, and you'll see the label is a 5. And so our goal today is a very classic machine learning problem. Essentially, we're going to try to predict what digit is in this image, like given the image, and this is the true label. So there are a total of 10 different digits, which are from 0 to 9, and basically we're going to predict this in a very simple model, which is called logistic regression. And so let's take a look at how logistic regression works. Oh, and by the way, the representation of this image is like, if you take a look at image that shape, this is a 28 by 28 image, so it's like 28 by 28 pixels, which kind of you can see from here. So yeah, logistic regression is very simple. But to start out, I'm going to have to, so if everyone's familiar with linear regression, you know you have this equation y equals mx plus b. So you have one output variable, you have one input variable, you have your slope, and you have your bias. So logistic regression is very similar with some key differences. So the first thing I'm going to do is create my m and my b essentially. And so form. So I'm basically just going to create this random weight matrix. It's going to be 28 by 28 in size. Where's it not defined? Cool. And right, this is not going to work. And so normally in something like NumPy, you guys are just used to doing this, right? You can just do numpy.random.uniform. You can pass in a shape, 28 by 28 and 10, and you'll just get back out. This should be bigger. There we go, that's what I wanted. And so you'll get back this big tensor. But the problem is in JAX, they actually do something really interesting that you may not be familiar with, and that is passing in an explicit pseudo-random number generator key. And the way you do that is the following. You make this RNG key here, which is equal to jax.random.prng key, and you give it a seed here. And so the way this works is you actually have to pass in the RNG key here in order to make your matrix W. So this may be very confusing to people who haven't worked with random numbers before. But essentially, in normal circumstances, your random numbers are generated by some pseudo-random process in the background, which uses various factors like sometimes the time and data on your computer, various other environmental factors, and basically it's very difficult to reproduce. Oh, she thinks it's this. I'm sorry, I didn't read that. No, we're not going to do that. Anyway, so these random factors make it really hard to reproduce results. Yeah, it's for all random functions, you have to pass in this RNG key. And so the idea is you want to be able to reproduce your results. You want to get the exact same randomness every time you call this function. You don't want it to change every single time. And so by passing around this explicit RNG key, you actually, this RNG key just basically looks like a pair of numbers. And if you start out with a different seed, you also get a pair of numbers. Yeah. And then, so this pair of numbers is basically the seed that helps you generate new random numbers. And so this way, your code is deterministic. You can reproduce your results, and your life will be much better. And of course, you don't want to use the same RNG key for every random function you call, so you usually do something like jax.random.split RNG. 1, 2. So now you have these two keys here that you can use, and so you'll use the first one to create your W, and you'll use the second one to create your bias. And so this seems like an unnecessarily complicated step. Oh, we just want to add the shape of 10. And actually, I'm going to initialize. Okay, lovely. And so the idea is you want reproducible results, and oh, she's don't apologize. That was a good suggestion. Anyway, you want reproducible results, and you want to be able to do have control of the randomness in your program. And so you have this key. And the general rule of thumb is you only want to pass the key to one function, and then you want to create a new key. And the way you do that is using the split function. So every time you want to use your RNG key, you have to split the key, use one value, and then continue using the other value for the rest of your program. this may seem excessively complicated, and I'll link you to some resources later about why this is important, but just take it as a fact for now. Cool, now we have our W and our B, and we're just going to do a linear function. And so here we have our image here. I don't know why Colab is so slow today. Anyway, so we can flatten this image and get one big long vector. And essentially, we're going to do a matrix multiply with this big long vector. Oh, the dot T is basically transposing your matrix, so I didn't explain that. So yeah, you take the shape, there should be of size 10, very easy, and then you just add your bias term. And boom, this is one more step. You add a softmax. And so I'll explain exactly why we do this here. Nice. And so I'm just going to call this function apply, which is, actually, let me first explain what this is. So in our final trained models, these logits are, these are actually called probabilities, but so in practice, these probabilities are going to be the probability that your digit is equal to whatever mth digit is. And so if you actually take a sum of this, this is going to equal 1. And so the argmax is going to represent which digit you think your prediction is going to be. And so essentially, our model is going to have to predict a high value for which is the true digit. And so I'm just going to put this into a little function, def apply. I will explain why I do params later. So yeah, you can pass in your W and your V and your image, and you get back these logits. So the reason I do params is you'll see commonly in this JAX library when you want to pass in parameters that you're trying to train. And so by training, I mean like updating based on the data. You'll call them params and you'll unpack them within the function. You'll see why this is helpful as we go along. I'm going to go a little bit faster and just assume that you have the basics of linear regression, but please stop me if there's anything that's weird. And so now we can define our loss function, which is cross entropy. And so so the cross entropy loss function is actually defined on some batch of data. And so actually I'll not do that for now, but instead let's focus on making this compatible with batches. And so right now we're able to pass in one image, but generally during training you want to pass in the whole data set, or at least a subset of a data set. And this is where vmap is super helpful. And so I'm just going to create this batch apply function, which is going to be just vmap of apply. So essentially, our parameters are going to stay the same for all the examples, but we're going to have a batch dimension at the end. And so now we can, once that vmap, we're going to also define our data loader. If you're not familiar with the data loader, this is just a convenient function that will create batches out of our data set. So in particular, I have this batch size here. Don't worry about this little bit of code. You may be familiar with it, you may not. Batch. Cool, so you can see here that we have 128 of these images, and so we can actually pass it into our apply function, our batch apply, and give it the params, which is W and V, and also the images, and you'll see the resulting shape is 128 of these predictions, which are each like a vector of size 10, as you expect. So works as you want. I am going to skip some of these details just so we can kind of get to the point. So these are functions that you can pretend that I wrote just now. But essentially, we're computing the cross entropy loss, which is like a function we're trying to minimize. Here, this function basically computes the loss with respect to our parameters. And so we pass in some parameters in the batch, and we compute this cross entropy loss. We can see the accuracy of our model so far, and I will explain this stuff afterwards. So cool, and then I'm just going to write a training step. I know I'm going a little bit quick just for the sake of time, but is there any questions about the things I've done? These are kind of basic machine learning steps. There's not really a machine learning workshop, just a showcase of how JAX works. Cool. So let's just define our training step, which we're all probably used to. And so given some parameters and a batch, we want to basically update our model parameters in order to fit it better to the data. And so actually we are interested in doing this update via the gradient, and so we're going to use our grad function. But actually, we want our loss value and our gradients. And so I'm going to use something called value and grad here, which basically takes the derivative and also gives you the value. So our function here is our loss function. Yeah, I think that's it. And then we can basically give it our parameters and our batch. And so I don't need to pass any extra arguments here because we're taking this derivative with respect to parameters. And we're going to update our parameters using something called JAX.tree multimap. So here's the key idea. You want to update each of these parameters with respect to the gradients. And so this is the operation. Oh, question here? No, cool. So the operation is essentially you're subtracting some multiple of the gradient. And you want to apply these to all your parameters. Now, this is a very simple model, but as your models get more complex, you can have nested objects of these arrays. And these nested objects are called PyTrees. And so a PyTree could be a list, it could be a tuple, it could be a dictionary, but essentially once you get down to it, the values are arrays. So for example, if our params is WB, we can consider params to be a PyTree where the leaves are W and B. So when we do a multi-map, essentially we want to apply some function to all the leaves of the variable, of the PyTree. And so in particular, we want to apply this SGD step to each of our leaves, and the SGD step takes in a parameter and a gradient, and so these are our set of our parameters and our gradients. And so actually, let me show you what this looks like. Cool. And so if you look at grad, this is just going to be a tuple of the same shape as our parameters. So yeah, our new parameters are going to have the exact same shape as our old parameters, but these values are going to be updated based on the gradients. Cool. And so yeah, I'm going to copy and paste our, oh, actually no, I don't need to. This is pretty simple. So I'm just going to put this into a little function. We can just basically return our new parameters. Yep.
So the multi-map thing, does it just apply it element-wise to every element within the parameters?
Exactly. Oh, not every element within the parameters. It's every. So let's suppose you have like a dict that's like A, and then you have some array, and then you have B, which is a list of array 2, array 3. And so multi-map will basically return something of the same structure where the function is applied to each of these arrays. Yeah.
Okay, makes sense.
Yeah. And so you can have any arbitrarily nested like dictionary list tuples, and it'll apply to all of them and return the same structure.
Okay, yeah.
We're just going to return the new parameters in the loss. And I'm going to copy and paste some code just so we can quickly show how this works. But yeah, this is very simple. So I'm initializing my weights and my bias, and I'm creating these parameters. I'm getting my data set just like I did before. Getting my data loader, which automatically batches my data. I'm going through each batch of my data, and I'm basically training my model and updating it each time. And hopefully, yeah. Oh, I made a mistake. It should not be negative. Oh no. Okay, I'm not going to debug it now, but it really shouldn't be negative, and I promise this works. And the one key thing I want to show you is, once you've done all this, this is, okay, I guess relatively fast, but if you really had some large data set or some large model, you just apply this decorator on top, JAX.JIT. And this is equivalent to doing train step equals JAX.JIT, train step. And this will compile your entire program end to end, and so this will be really quite fast. And so this works smoothly, and everything else will work as you expect. And you're not seeing a big difference now because it's a really small data set, but I promise it would be a larger difference otherwise. So apart from the machine learning concepts, does anyone have any questions about the way I use JAX? Okay, cool. Yeah, sorry, that example was a bit quicker than I had expected, but maybe some of these things will clear it up for you. And so that was basically a machine learning example using JAX, and I want to compare it to how it would go in PyTorch or TensorFlow, which maybe some of you are more familiar with. So some things you may have noticed is the first is JAX has the exact same API as NumPy or SciPy, which is really great if you're coming from those libraries, whereas PyTorch or TensorFlow have their own APIs. And you might notice that I didn't use any facilities built into the library to build these models or anything like that. And so JAX is really built for generic, numeric, or scientific computing, whereas PyTorch and TensorFlow are really specialized for machine learning. Both of these have automatic differentiation. As you saw, I was able to take gradients of my functions really easily. The one, I guess, first distinction between these two is the fact that they run on accelerators, but they're very different. PyTorch and TensorFlow both are compatible with running on GPUs and TPUs, but really, if you've ever worked with a TPU, it's kind of a pain to get running on either of these two libraries. Whereas in JAX, it's very simple. As you saw through my pmap example, like it really is that easy to get your code to run on these like distributed settings. The next thing is really first-class JIT. So if anyone's ever worked with TF function or torch script in PyTorch or TensorFlow, you know that it works, but sometimes it can be a pain, especially because they don't have the same restrictions JAX does. They don't require pure functions. You can have arbitrary code and side effects, and so the result is it's a little bit more finicky to make use of the just-in-time compilation. And it's not as fast because JAX uses XLA, unless you opt into XLA on these platforms. The next thing is first-class support for higher-order derivatives and gradients. This is not the function I showed within this workshop, but essentially, JAX has support for taking gradients of gradients of gradients of gradients. You can just keep chaining the grads and it'll just work just fine. Whereas in PyTorch and TensorFlow, it's possible, but usually the computation is actually not as efficient as in JAX. And also, this is even more apparent when you start computing more interesting functions. Like, for example, if you want the Jacobian or the Hessian of your function, this is available in PyTorch or TensorFlow, but really JAX was designed to efficiently compute Hessians and Jacobians for you, which is really great. The final point is JAX is like a relatively new experimental library. It's still in a research phase at Google, and so there's very little third-party support or other libraries that are built on top of it. Whereas PyTorch and TensorFlow have like a lot of third-party libraries and a lot of built-in functionality. Like as you saw, I had to define my own cross-entropy loss function, whereas in TensorFlow, that's already there. Any questions about some of these differences I talked about? These are kind of the key overviews. Cool. So that kind of begs the question, like, when should you use JAX? Obviously, it's not some general purpose hammer that you should use all the time. And so these are kind of the three situations, in my opinion, you should really consider using JAX. The first one is faster code, specifically on TPUs. You're not going to beat the performance of JAX using PyTorch or TensorFlow in general. JAX is very well optimized because of the XLA compiler, and the compiler just gets better and better. And so if you really need fast code, but you need it to be in Python, like JAX is really the way to go. I've seen real-time like fluid dynamic simulations and in JAX, which involves like solving partial differential equations in really high dimensions in real time, and it's like really amazing the stuff you can do. The next is if you really need these advanced functions like higher order gradients or forward mode auto-diff. And so before I mentioned that it was very efficient to compute Hessians and Jacobians, this is possible because of something called forward mode auto-differentiation. I won't explain this now, but essentially you can think of backwards mode as a chain rule. Forward mode is a different way of computing these values, which is really efficient when you need Jacobians or Hessians or et cetera. And the last reason is you just want to try something cool. This is kind of hip, and a lot of researchers are kind of moving, especially researchers that were working in TensorFlow before, were just kind of tired of how bloated and hard to use TensorFlow has become, have really moved to JAX and enjoyed it. And these are cases where you really shouldn't use JAX. And so the first one being just straightforward models and straightforward training just use PyTorch. They have so many built-in tools and so many facilities available to you. If you have something that's simple and straightforward and you don't need more performance, you don't need these extra features that JAX provides, it's really much easier to use PyTorch. The next thing is highly dynamic behavior. So I mentioned that this compilation step makes your code much more efficient, but this step has some constraints. And in particular, it kind of expects data to have a similar shape every time. And so the values may change, but the shapes stay relatively constant. And so if you are expecting your values to change drastically between runs, this is maybe not a good time to use anything that requires compilation because you're going to be constantly recompiling your graph. And finally, performance is not a big deal. Like if you don't care that you're getting this insane performance from the JIT, but you're happy with the performance you're getting in other libraries, you should stick with those other well-maintained libraries. I guess just a little extra is, why am I excited? Well, making the high-performance code easy and making the TPU training easy is really great. Like those two things have been more difficult in the past. And especially coming from languages like TensorFlow, which in order to reach that high performance sacrifices usability, I think this is a great mix of both worlds. And also functional programming. Like I mentioned, you have to have pure functions, and I think this is a great way to improve the clarity of your code and the clarity of your research, which is, when you have side effects and state in your more traditional programs, it's hard to reason about things as your projects grow. So for you guys, in terms of next steps, these are what I would do if I were you. So there are tons of demos on JAX's. Oh, actually, before I move on to this, is there any questions about the things I've said, the pros and cons? Yeah, sorry, I'm going a little bit quick, but yeah, it's just because it's over 8 and I don't want to take up too much of your time. But yeah, JAX has some great demos on their GitHub page. For example, they have their Sharp Edges notebook. Here they explain in detail some of the gotchas of JAX. So using pure functions, why do we have to use this random number generator, etc. And they have a lot of collabs explaining how to use TPUs or pmaps. And finally, they have like a nice end-to-end resonant 50 training example, which is kind of what everyone looks for when you're trying to get started. There's also some cool other JAX features that you may want to look into. For example, there's things called LAX operations, which are essentially low-level JAX operations that you can make use of to build your algorithms. And so, for example, one such LAX operation is called scan. And so if you're building a recurrent neural network, you want to process this input sequentially, and scan allows you to do that very quickly. And the final thing is like libraries like Stax, Flax, and Haiku. These are 3 like high-level libraries. You can kind of think of them like carrots, but really they're more on the level of PyTorch. And so these are useful abstractions for building these neural networks more efficiently and cleanly and with less mistakes. I didn't show you any of these today because it's kind of up to your preference about what you want to use, but they are available. And yeah, I will just show you what I think are useful JAX resources. And so if you go to I usually just, if you just search up JAX, you usually won't get the right result. You got to go search Google JAX. So here's their GitHub page. The TPU collabs are all here. You can take a look at these. There's some great examples here, including the Resonant 50 example. The reference docs, you can get these straight from here, but they have some great examples over here. And yeah, the reference documentation, I think I checked this before, but there's some really, these are pretty clear and easy to use. And in particular, I would suggest looking at the Sharp Bits notebook. I think it has some great information in there. So one last thing is, this presentation is really an intro. I really didn't teach you that much, right? I just gave you an overview of how JAX works and kind of why I enjoy using it. But really, it's great if we could work together, build projects together, and kind of learn JAX together. And so for now, the place to do that is Discord. And so we can join Discord and go to workshops, and I'll create a subsection for this workshop. We can move it off of Discord onto some other platform if people prefer, but this is really the place to go for now. And yeah, that was my presentation. Thanks for listening. Do you guys have any questions? Yeah, I know it was a bit fast in the end. I can definitely go over some things in more detail if people have more time and want to stick around after the workshop. No questions? Okay, I will also put in my email. I know I said Twitter only in the beginning, but I guess that's not reasonable. Oh, no problem if she thinks. Let me, here is my email. Yeah, so feel free to reach out to me at any time and ask any questions you'd like. Thanks for coming. Oh, yeah, quick question, Matthew.
I wasn't here at the start, so I probably missed it, but what exactly would parallelizing over certain dimensions look like for those like vectorized maps? Is it just like how many like threads you use for computing, or?
Sorry, could you repeat that last part? So you're asking for what exactly a vectorized map does?
I mean, when you define the axes over which you parallelize, what exactly are you achieving by modifying like these values in axes?
Sure. Yeah. So yeah, I'll go back to this example here. And so just to refresh, sorry, let me get this going. Cool. So normally we have this function f that takes in these single values a, b, and x. And then so your goal is you want to pass in several x's. And so this set of x's, and you want to compute this function f for all these x's. And so some ways you can do this, of course, are like looping over it or something like that, which is quite slow. So really you want to do this in parallel. And so your question was specifically about why we use this in-axis and what it does. And so essentially each element of this tuple corresponds to one of these elements, the arguments, and we're basically stating the following. We're telling JAX which axis we're like replicating, and so here we're telling JAX that the final axis is being replicated, and we're telling X like what the axis of replication is. So let me show you maybe a slightly different example. Let me define some function f which takes in let's say capital A, B, and C, right? Actually, so it's capital A and B, and then we basically return like the matrix multiply of A, B. So we can do, this is just an array, 1, 2, 3, 2, 3, whatever. Sorry, the sparks are kind of annoying. I didn't turn that off. So we have f of A and B. This should return a matrix. The slowness is caused by, yeah, sometimes you don't get the best runtime when using Colab. It's really hit or miss, which is, I guess, why it's free. Cool. So let's say now we wanted like a bunch of B's, and so in particular we wanted, like we can make B, so we wanted a bunch of B's, and so we know these are 2 by 2 matrices. Let's say we wanted like 5 of them. So we know that we're not replicating A, but we are replicating B, and we know that our duplication of 5 is on the final axis here, which is a 0, 1 second axis. And so by specifying that it's 2, essentially JAX will know that the parallel. I think I lied to you. Why is this 1? That should not have worked. Okay, I'm not sure why this example is not working, but essentially, in general, like if your batch dimension is at the end, oh, I'm using B, that's fine, no wonder it's silly. Okay. There we go. And so we know that our batch dimension is at the end, and so we're just specifying that, yeah, like this is the second axis, second dimension here that we're using. And so when we get the resulting shape, we can actually also specify an out axis. And so we're specifying that you want the batch to also be at the end here. So for example, if you put it at 1, it'll stack it up in the middle dimension, or if you put it at 0, it'll stack it up at the dimension here. Does that answer your question? Does that clarify things?
Somewhat. And when it stacks up there, it's just like, I guess, yeah.
Hold on, I can show you how that looks. JAX dot. Let me actually make this manually. I can do this here. Okay, so 2, 2. Hold on, give me a sec. So this is one of these matrices, and we have another one of these matrices, and then we have a final one of these matrices. Hold on, hopefully I can illustrate this. Just going to make a bunch of ones, and so it's easier to see. Cool. So when we take a look at this, 2 and 3. Sorry, hold on, let me just make this work. Oh, yeah, that's a problem. The batch dimension is at 0 now because I put it at the beginning. And so yeah, so as you can see, like when the batch dimension is at 0, you get like each one of these entries corresponds to one of these matrices I've made here. But if you switch the batch dimension to 1, for example, the layout is different, right? Where like the first, you kind of get the first row of each matrix, then the second row of each matrix, then the third row. Or if you put the batch dimension at the end. Yeah, exactly. It just changes the arrangement of how these things come in. In general, when you're working in machine learning code, your batch dimension almost always comes at the front because that's just the most convenient and straightforward thing to do. Sorry, I closed everything. Let me see if I can open these up again. Yeah, so in general, you put it at the front, and that just makes the most sense visually and intuitively. Does that kind of clear up your question a little bit?
Yeah.
I think if you check out some more machine learning code, maybe you can message me afterward. I can send an example. You'll see why batches are important. Any other questions? I guess only 2 people left. Cool, great. Thanks for coming, everyone.